Permutations and combinations are very useful, and we're going to see here how we can use Vedic mathematics to evaluate them. So first of all, just a quick explanation of what we mean by these terms. Suppose we want to know how many arrangements there are of two letters chosen from four letters, say A, B, C, D. The convention is to write this like this, 4p2. So it's a permutation, because we're asked about an arrangement of letters, and we're choosing two things out of four things, so the numbers are written on the left and right like that. Well, in this particular case, we've got four choices for the first letter, and with each of those four choices, there are three that can follow it. So the answer is 4 times 3, which is 12, and they're listed here. So here you can see the ones that start with an A, and there are three choices following it, and so on with the other letters. So we get 12 altogether. The easy way to get these numbers, 4 and 3, from these numbers, 4 and 2, is to say, well, it's going to start with a 4, the first number here, and then there are two numbers multiplied together. So we can say there are two numbers running down from 4 times 3. So in the case of 10p3, we'll say there are three numbers running down from 10, so that will be 10 times 9 times 8. And that's the number of ways of arranging three objects chosen from 10 objects. 10 times 9 times 8, that comes to 720. So for permutations, the order is important. AB is considered to be different to BA, for example, and so on with the others. When we come to combinations, the order is not significant. That's the difference between the two. So if we're asked how many selections are there of two letters chosen from the four letters A, B, C, D, the order is not significant because we're just asked for a selection. And we write this as 4c2, the number of ways of selecting two things out of four things. So in this particular case, you've got A, B, C, D, and we know there are 4 times 3 ways of arranging them if the order was significant. But because the order is not significant, we need to divide by 2. In other words, it's just this top row here. And this works out to 6. And these are the 6, it's just the top row here, because the order is not significant, and so we only get these 6. And that's why we divide our 12 by 2 here. Similarly, if we wanted 10c3, that would be the 10 times 9 times 8 that we had before, but divided by 3 times 2 times 1, which is called 3 factorial. 3 factorial means 3 times 2 times 1, 2 factorial means 2 times 1, and so on. 4 factorial is 4 times 3 times 2 times 1. Or we can do some cancelling. That cancel the 3 and the 2 with the 9 and the 8. You get 10 times 3 times 4, which is 120. Our base multiplication is a topic from Vedic mathematics. Suppose that we want to find 97p2. That means two numbers multiplied together from 97 downwards. So that means 97 times 96. So clearly we can do base multiplication for that because the numbers are both near to 100, and I'll assume you're familiar with this. We simply take the deficiencies of the numbers from 100, cross-subtract to get the first part of the answer, and multiply vertically to get the last part. So the answer is 9312. And this comes under the sutra, all from 9 and the last from 10. Now here's another example, 204b2. Here we've got two numbers multiplied together from 204 downwards, so that's 204 times 203, and again we can use base multiplication. So without explaining it too much, we have one deficiency added to the other number, and because the base is 200 here we have to multiply by 2, and this is the product of the deficiencies. So these are the two parts of the answer, and we get 414, 12, which is there for the answer. If we had a combination, 49c3, We know that that means three numbers from 49 downwards multiplied together, divided by 3 factorial, 3 times 2 times 1. Well, that's a 6 on the bottom there, so we can cancel it with the 48 to leave 8. And that 8, if we look at the other numbers, the 49 and the 47, means we could give a factor of 2 to this one and a factor of 2 to this one to make them both near to 100. In other words, the 49 becomes 98, the 47 becomes 94, and we've got another 2. So we can use base multiplication on this and then double. 9212 times 2, 18424. 13p7. Here we've got 7 numbers multiplied together from 13 downwards. What's the most efficient way to work this out? Well, you've got a choice really, but one might be to pair the numbers up. So because 13 times 7 is close to 100, it's 91, we can put those together. And then the 12 times the 8 is 96, and 11 times 9 is 99, and that just leaves the 10. So here we've got 3 numbers near a base of 100, and again we can use our base multiplication to do that multiplication. Here it is. There's the 3 numbers near 100. These are the deficiencies. We cross-subtract 91, take away the other deficiencies. We multiply these deficiencies together in pairs and add to get the 49, and we multiply the deficiencies to get minus 36, which gives us this number. So because we've got to multiply by 10, our final answer is 8648,640. And this is algebraic proof of that method. Now, another useful Vedic method is the special numbers, which come under the sutra by mere observation. This is where we've got a number like, say, 1001, which happens to have special properties, so it's called a special number. And one of its special properties is that it's got some nice factors. It's 7 times 11 times 13, which is very handy for us. Also, it's a number which is very easy to multiply by. So if you've got, say, 346 multiplied by 1001, the effect of that is simply to make the number repeat itself. So we get 346, 346. So any number gets repeated like that. If we only had 34, then you can imagine a 0 in front, so we've got 3 figures like we had here. So you'd have 034, 034 when you multiplied, and the initial 0 would be dropped off. So we get 34034. If you had more figures here than 3, because this is a base of 1000, so 3 figures is the easiest case, you'd need to do a carry. So you'd have the 3, 4, 5, 6 repeated, but this 3 will get carried over to the 6, and we get 3, 4, 5, 9, 4, 5, 6. This is very handy, and there are quite a lot of these special numbers that we can make use of. Let's look again at the 13p7 that we had before, which was this sequence of numbers multiplied together. In fact, we've got 7, 11 and 13 in there, and so we can make use of this 1001 number. What's left after you've taken those 3 out is the 12, the 9, the 8 and the 10. Put the 10 last because it's easiest to multiply by. So we're going to multiply here, 12 times 9 times 8, 108 times 8, that's 864, times 1001 times 10. So the 864 gets repeated, 864, 864, and the 10 gives us the 0 on the end. So there are a lot of these special numbers, and they're really worth knowing, because if you're doing simple arithmetic, mental arithmetic, it's very handy to know these, or some of them. This is only some of them here. Let's take 26c4. That means 4 numbers from 26 downwards, like that, divided by 4 factorial, 4 times 3 times 2 times 1. Well, if we look carefully at these numbers, we might notice that we've got 23 times 13 contained in it. We've We've got the 23 here, and this is twice 13. So when we do our cancelling, we should try and leave those intact. In fact, this is 24 on the bottom, which could cancel with that 24 and leave us with 26 times 25 times 23. So if we take out the 23 times 13, which we know is 30 bar 1, 30 bar 1 of course is 299, it's one below 300. So we get 30 bar 1, and we've still got a 2 and a 50 factors to include, so times 50. So we multiply those out and remove the bar numbers 14950. Another handy type of multiplication which we use in the Vedic system, and which comes under the sutra by one more than the one before, is where we're multiplying numbers like this, where the first numbers are the same, 6 in this case, and the last total 10. 2 and 8 is 10. And we apply the sutra by one more than the one before, which means we multiply the initial 6 by the number 1 more. So 6 times 7, which is 42. And then we multiply the last by the last. 2 times 8 is 16. And we get the answer very easily. So we're making use of this technique as well. Given, for example, 46p3, that's 46 times 45 times 44. And notice the 46 and the 44 come under this particular sutra, this particular type of multiplication. So we can multiply those. 4 times 5, the next number after 4 is 5, is 20, and 6 times 4 is the 24, and we've still got the 45. Because 45 obviously is a 5, I'm going to double that and halve this one to get this product, which is the same, and then it's easy to multiply this by 9 and put the 0 on. Let's just look at one or two more examples. 37p3, 3 numbers from 37 downwards. Well, one of our special numbers was actually 111, which is 37 times 3. So that's handy, we can use that here. There's a factor of 3 we can use from here. So the 37 times the 3 gives us 111. What's left? We've got a 12 and a 35. Well, because 111 is close to 100, it makes sense to try and take one or two of the factors from the 12 to give us another number near 100 when we multiply by 35. And so we take the 3 out of that 12 to multiply by 35 and give us 105, which leaves us a factor of 4. So this is now easy to do with base multiplication. We multiply that by 4 and we've got the answer. 18p5, 5 numbers from 18 downwards, like that. What can we do with this? Well, we can get products near 100 again. We can take 17 and a 6 out of here, which gives us 102. Let's write this down. 17 times 6, and 15 times 7 is also contained in here, which is close to 100. And that leaves 16 times 6, which happens to be also close to 100. So we end up with this, and that's easy to do with base multiplication, to get that and then the answer. Now we come to a special case. We know in the Vedic system that we've got special cases that come up. If you happen to spot them, then there's an easy way of getting the answer using a special device. And this is for permutations of this type, where we've got 4 numbers running down from a number which is 1 below a multiple of 5. So it's illustrated here. Here we've got 4 numbers running down from 1 below a multiple of 5. 19 is 1 below 20, 14 is 1 below 15, and there are 4 numbers. So multiplying 4 consecutive numbers like this is actually easy, and we'll take the 14p4 first of all, which is this one here. 4 numbers running down from 14. What does it mean? It means this. If we multiply the outer pair and the inner pair, we get 154 for the outer pair and 156 for the inner pair. Now this is a special type of multiplication that we just considered, because the first figures, the 15, are the same, and the last add up to 10. And you'll remember that the method was to multiply the first figures, the 15, by the number 1 more. So 15 times 16 is the first part, and then the 4 times the 6 is the last part. So we get the answer 24024. Similarly, if we take 19p4, which happens to be this sequence of 4 numbers here, here it is, we can take the outer product, 19 times 16, which is 304, and because we know it's this type of multiplication, we don't need to work the other one out. We know it's going to actually be 2 more. It's going to be 306 for the product of the inner pair. And then we've got, of course, 34 and 30 and 6. And so we multiply 30 times 31, and 4 times 6 is 24. And we'll work that out. In fact, these permutations always end in 24. In fact, they always end in 024. So that's something worth looking out for. Here's another example. We don't always have to apply it when we've got just 4 numbers multiplied together. Here we've got 5 numbers. But we notice that contained within our string of numbers there is one of our special type. So the 19, 18, 17, 16, we know a special way of working it out. So we do that and multiply it by 20. We did that on the previous slide. 36C7 is this. Do we have this special case contained in there? Well, there's the 35, which is a multiple of 5, and the 4 numbers following it are easily found using this method. So we can apply this, and so we want to leave those numbers intact in our cancelling. So what we could do is take the 7 times the 5 to cancel with the 35, and the 6 times 3 times 2, which comes to 36, cancels with the 36, and the 4 is left. So what you get is the 34 times 33 times 32 times 31 times the 30, which is left there, and the 4, which is left there underneath. So we work this out. Let's take the product of the outer pair. That's 1054, and so the other number is 1056 times 30 over 4. So we've got 105 times 106 times, and the 24 times the 30 over 4. Obviously we use base multiplication on this. 1113024 times 30 over 4. So it's easy enough to multiply by 30 and divide by 4. Now some of these permutations and combinations can be very large numbers, especially the permutations. And so even a calculator will give you an approximation to the answer. This comes under the sutra special and general. I'm going to use this special number, 2 to the 10 is 1024. So suppose you want 25p11. This is the product of 11 numbers from 25 downwards, and it's actually a very large number with 15 digits. What we can do is to use the average in this case. In the middle here we've got 20, so we could say that the product of these numbers is close to a 20 multiplied by itself 11 times. So 20 to the power 11 is an approximation. Well, 20 to the power 11 is 2 to the 11 times 10 to the 11, and because we know 2 to the 10 is 1024, which we could take as being 1000, 2 to the 11 would be twice that, which is 2000. In fact, 2048 times 10 to the 11, which is about 2 times 10 to the 14. So we can use the average to find permutations and combinations which are large numbers. Let's take 19p6. Here we've got 6 numbers from 19 downwards. It's not such a big number, but we could look in the middle and we notice that, well, there isn't a middle number. We could take the 16 though, which happens to be 2 to the power 4, and make use of that. So imagine that we've got 16 multiplied by itself 6 times. That should be close to this product here. And 16 is 2 to the power 4, so we get 2 to the 24, which, using our 2 to the 10, could be 2 to the 10 squared times 2 to the 4. So this is about 1,000. Squared will make it 1,000,000. So this is 16. We've got 16 million. And in fact, the answer is this number here. It's about 19.5 million. We've seen how we can use base multiplication and the special numbers to efficiently get products of series of numbers. We've seen a special case where there are a product of 4 numbers involved, running down from one below a multiple of 5. And we've seen that we can also get approximate values by using the average of a series of numbers. Thank you.